Okay, hi Year 11. So today's video is going to have a little bit of a look at 15D, which are identities in Pascal's triangle. So there's a lot of patterns within Pascal's triangle, and it is possible to identify and prove the existence of some of these. Now, we haven't done a lot of proofs yet, so we're basically just going to have a look at some simple proofs, and in which we need to just make the left-hand side be equal to the right-hand side. So I'm going to scroll down in your OneNote, and we're going to have a look at these other things in a moment, but I want to have a look at this section here, just some common questions. So I guess in general, there are usually only three options for questions. The first one being to substitute in a value for x is what we can do to help us out. And we're going to have a look at some differentiation and integration options. Now, if you're in the accelerated class, then you will be able to do these now. If you're not, then you'll have to do the proofs that involve differentiation and integration at a later date because you haven't done that yet. So I want to have a look at two of these. Actually, I think there's three below. And the first proof here is saying, prove that the sum of the coefficients in this expansion, a plus b to the n, is equal to 2 to the n. So we want to prove that the sum of the coefficients of a plus b to the n is equal to something. Let's just write out what a plus b to the power of n is in a generalized format. Okay, so I've just jumped over to your HSC formula sheet on the last page with combinatorics, and there's actually the expansion there given to you. That they've got it in terms of x plus a, but we could write that in terms of a plus b to the n and expand that out. So instead of having our NCRs, we've written that in the bracket format in here. So let's write an expansion on our page for a plus b to the power of n and use that as our basis. So a plus b to the n is equal to, so let's think what our coefficients are doing. We're starting with NC0 and our coefficients are moving along up to NCN at the other end. Our powers of A are starting with A to the N and B has got B to the 0. Our second term will be NC1. A is decreasing in power from N to N minus 1 and our B is increasing in power. So all along there, our powers, n minus 1 plus 1 must equal n, n plus 0 must equal n. So we're moving along until we get to our last term, which will be NCN, in which case our A will have a power of 0 and our B will have a power of n. So that's what the expansion looks like, but that is also able to be written as the sum. Remember, this means sum of, and it's the Greek letter called sigma. So it's the sum of things. So we're basically summing all our NCRs, and we're going to have A to the N, B to the N minus R. That's basically an expansion of what this is, but we're trying to prove that this thing here that we've expanded is equal to 2n. So we need to sub in something. So we would like this part in here to be equal to 2, and then I want to prove the sum of the coefficients. So then we want to make sure that we're actually getting the sum of our coefficients in there. So let's do that. Let's let A equal B equal 1. And that relates up to here to our first thing where we're going to substitute in a value for x. So on the left-hand side, we're going to get 1 plus 1 to the n. And on the right-hand side, we're going to end up with NC0. And we're going to have 1 to the power of n. Well, 1 to the power of anything is still 1. And b to the 0 is 1. So we're going to just end up with NC0. So let's just neaten that up underneath as we go. So 2 to the n is NC0. We're then going to have NC1. And we're still going to have 1 to the 1 and 1 to the something minus 1. So we're still going to have 1. So we next get NC1. So if I keep going with that pattern, I'm going to end up with my last term as being NCN. Probably didn't need that other line in there. So what I've got on my left-hand side there is 2 to the power of n, and what I've got on my right-hand side is all my NCRs, so all my coefficients of this expansion up here. So what have we wanted to prove? Let's check we've done it. Prove that the sum of the coefficients of a plus b to the n, yep, we've got that, is equal to 2 to the n. So we've actually proved it. I'm just going to write in there, is equal to the sum of the coefficients. So it's just a beginning style proof. We'll get a lot harder as we go through. But let's see how we go with our next one. Okay, now we're going to be continuing to see this sigma. Okay, so it's fairly new to us, and what we've got happening in this question is if 1 plus x to the n, which we can write in expanded form, is equal to the sum from r equals 0 to n, so that just basically means our first term would happen when r is equal to 0, and that would be n c0 x to the 0. Our second term would happen when r is 1, so we'd get nc1 x to the 1 all the way up to ncn x to the n. So all that sum is doing is showing us a shorthand version of an expansion. So we're saying if this is equal to this, show that this part here on the left is equal to this. So let's just deal with this first part. If 1 plus x to the n is equal to the sum from r equals 0 to n of ncr x to the r. Okay, so this is a fairly straightforward one. So let's look at what we've got. So if I've got this and I want to show this, we can see that my left-hand side over here could be made look like my right-hand side if I let x equal to 3. So if I popped a 3 in here for x, I'd have 1 plus 3 is 4, and that would give me 4 to the n. So in this case, that's what I want to do. I would like to let x be equal to 3. And then my left-hand side, I'm going to write that as left-hand side, is going to give me 1 plus 3 to the n. And my right-hand side, actually I might get rid of the left-hand side because we don't really need that in there, is going to be equal to the sum from r equals 0 to n of NCR, but we can write our NCRs like that. And the only thing I've changed is my x is 3. So 3 to the r. And that looks exactly the same as what's up here. It's just the other way around. So let's just neaten it up. And all right, so 4 to the n, which I've calculated from 1 plus 3, is the sum from r equals 0 to n of 3 to the r NCR. It's fairly straightforward. Okay, let's have a look at the next one. Now, if you haven't done calculus yet, this is not for you. If you're in my accelerated group of kids, you've done it, so it's going to work for us. So we want to say that if 1 plus x to the n is equal to the sum of NCR x to the r, which we've looked at above, we want to show that this is the case. Okay, so we've got r, NCR, and n 2 to the n minus 1. So what we need to do is, I think, let's write out an expansion for what we've got up here. So let's write out 1 plus x to the n. We know it equals the sum of r equals 0 to n of NCR x to the r, but let's write it out in a longhand format. So we're starting with NC0. We've got 1 to the n, x to the 0, plus NC1. We're going to have x to the 1. And although I put 1 to the n there, we might just get rid of that because it's just going to be 1 all the way through. So NC2, x to the 2, all the way up to NCN x to the n. So that's what our expansion is. So what we want to look at is what's happening here is we've got an r down the front and an n down the front. So let's think, well, how would we get that down to the front? we would use calculus and do our first derivative. So let's think of what we would be doing on our left-hand side here. My n would come down. I'd have 1 plus x to the n minus 1. And I'm just going to look at the expansion, not look at the expansion side. I'm going to differentiate this expansion here. So what I would actually have would be, this x to the 0 is just 1. So I don't actually need that x to the 0 there. And this NC0 is a constant. It's a number. So when we differentiate a number, it goes away. So the first term we're going to be dealing with here is NC1x to the 1. When I differentiate that, I end up with just NC1. My next term here, that 2, comes down the front, because remember, NC2 is a number. So I get 2 NC2 x to the 2 minus 1, which is 1. Plus, if I had another term in there, x cubed, I would have 3 NC3 x to the 2. My last term would become n NCN x to the n minus 1. I'm nearly there with my proof. What you will see is this side here, n times 1 plus x to the n minus 1, looks very similar to this part here. If I let my x be equal to 1, I will end up with 2. So let's let x equal 1. So I get n to the, in here, 1 plus 1 is 2. So I get 2 to the n minus 1 is equal to NC1 plus 2 lots of NC2, and I've let x be 1, plus 3 lots of NC3, and my x's are all 1, so 1 to any power is just 1, so I'm basically letting the x's disappear in that sense. And my last term is going to be n lots of NCN. So looking at what we've got here, my left-hand side here, n times 2 to the n minus 1, is the same as up here, and that is equal to the sum of my NCRs, starting at R is 1, which we've got here, and we're timesing that by R along the way. So in this case, R would be 1, R would be 2, and that would match my lower number there. So I can write that as the sum of R equals 1 to n of R n CR. Just make sure at the start you change that R there to a 1 because it won't work for 0.